Hello. So in this video we are going to be looking at methods of proof. So last time we looked at the idea of a proof, the main idea that we start from something that we know, we do a series of steps, and then we could do some more steps and more steps and more steps, and then eventually we get to what we want to prove, right? And again, that sort of idea will continue in this section. However, some proofs are not easy to do that way, in a direct manner, by just going straight from the statement and then going on from there. Sometimes you have to be a bit more creative and look at other ways of doing things, and that's what we're going to look at in this section. Different methods or different ways of doing a proof, which helps with proving particular statements that are a bit more difficult to prove otherwise. And so what I'm going to do then in this video is there are three distinct different types of proof I've noticed in this section. So it's a bit weird, it's a bit different, this video will be to the others. Instead of doing everything in one and then doing some examples, I'm going to split this up into three different sections corresponding to each different type of proof. I think that's the best way to organise it, and I will time stamp it. But yeah, and this is a topic as well that a lot of students tend to struggle with, or they just really don't like, and some of them even they say they don't attempt the question. So hopefully from this video it'll help. It'll give you a bit more confidence with tackling these sort of questions. Okay, so the first one we're going to look at is something called proof by proof by exhaustion. What that means is, from a statement that we want to prove, we get given something, right? And what we're going to do is actually we're going to split things into different cases. That's what exhaustion is. You create different cases, and the idea is that you exhaust all the cases, right? That it's true for every single case, and therefore then that every single case is proven. That means it has to be true for everything then, right? So therefore we prove it that way. So it's more of a different roundabout way of proving it rather than directly. So we split it into cases and then do it case by case. But that's a way we can prove it, and it helps, particularly with stuff to do with multiples or divisibilities, prove that something is even or something like that. And a very common technique we'll see in a minute is splitting stuff into odd and even numbers or different multiples or something like that. Okay, with that in mind then, so I'm going to say you split into different cases, then you prove each case separately. Okay, and that's what we'll be doing. Okay, and it doesn't have to just be even and odds. It can be literally just substitute. Say if we have to prove between, say, a statement between 1 and 10 or something like that, right? I don't know, between 9, and say that and that the square numbers between 1 and 9 are below 100, or 2 digits. Below 100, right? So then what you could do in that case is literally do 1 squared, 2 squared, 3 squared, 4 squared, up to 9 squared, and then you show that way they're all below 100. Just a very, very simple proof of that. But literally what you can do then is just substitute all the numbers in, okay? And that'll be different cases as well. And we will see an example like that, where you literally just substitute all the numbers you need to consider, right? Normally that isn't the best idea, because obviously they're infinite numbers, but sometimes it can be helpful to just substitute all the numbers you need to consider, and then it's true for every number, therefore be proving it. Okay. But I'm going to go back to even and odds very quickly before we look at our first set of examples. And it's very, very good idea, and you really ought to know based on the questions in exams how we express or define an odd or an even. And so even, first of all, is we can write any even number. So remember, these are numbers that are 2, 4, 6, 8 and so on. Or even we can go down to 0 and then -2, and then from that side from the negatives as well. So any numbers that are like that, and they are multiples of 2, okay? So they're multiples of 2. That means then we can write any even number algebraically in the form 2k, where we say k is an integer, okay? So that means if I substitute any integer k, remember an integer is literally just 1, 2, 3, 4, 5, 6, and then 0, -1, -2, -3, whole numbers, right? We looked at this very briefly when we looked at functions, I think. But that's what an integer is. And if I substitute any integer for k, say if k was 0, 2k would then be 0 as well. If k was 1, 2k would be 2 times 1, which is 2. K is 2. 2 times 2k would then be 4. 2 times 2 is 4. And then you can see, hopefully, as we substitute values of k, we get the multiples of 2. Okay? So that is a way we can express an even number in the form 2 to the k. And then the other one is odds, right? So odd is basically not a multiple 2. And so these are numbers like 1, 3, 5, 7, ... And then again we go back the other way and go -1, -3, and so on as well. And how we write this then is, well, think about it, an even number, every even number can be written as this. But then every odd then, couldn't we just then add 1, right? If we do 2k add 1, then that means we get an even number from 2k and then we add 1 to it, we should then get an odd, right? Because if we add 2, 4, 6, 8, ... then if we add 1 to all of these, we get 3, 5, 7, 9. Well, hang on, that's just a list of odd numbers then. So therefore, again, when k is an integer, any integer, but in general, we can write an odd number in that way. Okay, so realising we can write even and odds in this way will be very helpful with some of the proofs we do in a moment. Okay, right, so we can use this. We can prove statements involving multiples or divisibility by considering different cases. So what we're going to do is consider even numbers and odd numbers, which are two possibilities for a whole number, right? You can either have an even number or an odd number. So let's have a look at this example then. We want to prove that all square numbers are either a multiple of 4 or one more than a multiple of 4. Okay, so square numbers then is in the form n squared, right? Now, if I just add n squared, that tells me nothing. It doesn't tell me anything about being a multiple of 4 or anything like that. What we then need to do is, if we can't deduce anything from that expression, this n squared, we then need to consider n, which again is just a square. N itself is just an integer, right? N is either even or odd, right? Because n is a whole number, and then we're squaring it to get a square number. So n is either even and odd, so that's what we're going to consider then. So we break it then into two cases. Firstly, n is even, and I do recommend you do the even case first, because first of all it's easier, and second of all, if this method doesn't work, and we will see some examples where pulling it as even and odd doesn't tell us anything, then you can quickly spot that that it won't work, because even is simpler to work with. Anyway, firstly, if n is even, that means n can be written in the form 2 to the k, right? And I'll say k is an integer here. Right, hopefully, as we just discussed, I recognise that. We can write it, because say if n is even, we can write it in this form, okay? Okay, well then what we're going to do, well, we need to then consider n squared, right? So then, therefore, n squared here is 2k all squared, and that'd be 4k squared. Well, there we are then. It has to be a multiple of 4. We could say, we can emphasise this by factoring 4 out. So 4 lots of k squared. Wow, that's a multiple of 4 because you're multiplying by 4, really. So therefore, n squared is a multiple of 4 here. And that's that case proven, right? So we got the result we wanted when k is even. So it's a multiple of 4. Now, what about the second case? Well, if n is even, the other possibility is n is odd, right? Right, okay. So then n would be then 2k plus 1. By the way, you can have minus 1 instead. You still get an odd number. It doesn't matter, but I tend to like write plus 1. And again, that's when k is an integer. Right, okay. So then again, if that's n now, if we express n as an odd number, then that squared is going to be 2k plus 1 all squared. Now, see how I said even is easier to work with, because often with odd numbers, you get a harsher bracket to work with. So we're going to have to expand this now. But that would be then 4k squared, then 2k and another 2k would be 4k, and then 1 squared is just plus 1. Right, okay, well then, I'd start my question. It's either multiple 4, that would mean I can factorise 4 out of every term, but I can't factorise 4 out of 1. Right, so then I look at the other possible, so it can't be a multiple 4. 1 more than a multiple 4, okay. Well then, let's consider factoring 4 out of here. So 4 of k squared at k, then we add 1. Well, there we are then. Because k squared at k is an integer. So this is 4 lots of a number, so it's a multiple of 4. But then we're adding 1 to it. So therefore it's 1 more than a multiple of 4, okay? If I was to express that really clearly, if I said let n be k squared at k, then n squared would be 4m add 1, right? But hopefully you can see very clearly it's a multiple of 4 and 1 more. Therefore then, hopefully then you can see that n squared in this case is then 1 more than a multiple of 4. So there we are then. So we either got in either case that is a multiple of 4 or 1 more than a multiple of 4. So therefore in general, all square numbers, n squared, right, is a multiple 4 or 1 more than a multiple 4. So therefore all square numbers are either a multiple 4 or 1 more than a multiple 4. I do recommend restating stating the conclusion by restating the answer that they want you to prove. Just so you get all the marks. Depends how funny the marks scheme is. If you don't write a conclusive statement, I don't know, but I tend to do that. But there we are. So yeah, that is the strategy with these sort of questions. Basically, you're going to look for something to factor out more times than often than not. The main idea with these sort of questions is you want to factorise something, which will show it's a multiple of something. So like here, we tried to factorise a 4 out wherever we could, because it's talking about being a multiple of 4. Right, okay. So have a look at some more questions. Okay, this one then says use proof by exhaustion to show that for all n that is this big N. Now what does that mean, that N here? A brief reminder, we looked at it in the functions chapter earlier, really early on in the course. But this little weird N symbol there means the natural numbers. What that means is simply the list of numbers. 1, 2, 3, 4, da, da, da. So it's a list of positive whole numbers, essentially. So yeah, you do see a notation like that, but don't be freaked out, because it's just referring to positive integers. And also, n has to be less than or equal to 4. Well, actually, that tells us quite a lot. If n has to be a positive integer, and it has to be less than or equal to 4, well, that means then that n can only be 1, 2, 3, and 4, right? From this list, between 1 and 4, those are the only values of n we can get. So then it wants to prove then that n plus 1 cubed is greater than 3 to the n. So this is where exhaustion kicks in, because then you can you only need to consider these 4 numbers, right? As we discussed, that's what that notation means. It has to be a positive integer which is less than 4, which gets us these 4 values, okay? So really the difficulty is actually understanding the notation there, but there we are. So if we only got 4 values then, really n can be, maybe just consider the 4 cases that n is 1, 2, 3 or 4. So therefore then, the first case is simply n could be 1, well then just substitute that in. So n plus 1 cubed is 1 plus 1 cubed. That's 2 cubed, which is 8. And that's great. And also 3 to the 1 is 3. Well, therefore 8 is greater than 3. Clearly. So, statement is true when n equals 1. Okay? Because the statement being again, why have I considered these random numbers again? Because it wants n plus 1 cubed on the left. That's what I computed. N was 1. 1 plus 1 cubed is 8. Then 3 to the n on the right. Well, that's 3 to the power of 1, which is 3. So therefore, I then can see that 8 is greater than 3. So the left side is indeed greater than the right. So that statement here is true for the when n is 1. Then the second case then, well, the other number could be 2, right? So we're just going off the list of values here. So if n is 2, then we get, well, firstly then, n plus 1 cubed is 2 plus 1 cubed. That's 3 cubed, which is 27. Yep. And also 3 to the n would be 3 squared, but that's 9. So therefore, well, we can deduce that 27 is actually greater than 9, so it is indeed true. So statement is true when n is 2. Third case, oh, that have much room here. Case 3, well, then that n could be 3. So that's the other value n could be. So therefore, n plus 1 cubed is now 3 plus 1 cubed, which is 4 cubed, which is 64. And also 3 to the 4 is 80. Oh, hang on. Oh, no, 3 to the 3, sorry. 3 cubed is 27. So therefore we can say that 64 is greater than 27. So statement is also true when n is 3. The fourth case I'm going to have to write up here somewhere. I'll write my I'll write my list of values there, and I'm going to make room here. So the fourth option is either n is 4. That's the only other number it could be. So then, well, n plus 1 cubed would be 4 plus 1 cubed, cubed, which is 5 cubed, which is 125. And also 3 to the 4 is 81. And then, well, we can spot that that 125 is actually indeed greater than 81. So statement is also true when n is 4. Well, therefore then, statement is true for all is true for all values of n. Remember, the values of n are between 1, 2, 3 and 4. So there we are. The proof is done. So we've shown that this is indeed true for n is 1, 2, 3 and 4. Okay. So again, I think the trickiest thing is actually spotting the notation and spotting that you should split the values of n to these 4 numbers only, and then you literally just substitute them in. But that's the idea of exhaustion, right? It could be as simple as that, essentially. It could be as simple as just substituting numbers in. But there we are. Cool. Let's have a look at this question then. Now we need to prove that for all integers n squared of 2 is not divisible by 4. Right, okay. N squared of 2. Now, from this right off the bat, we can't do anything to this to show it's not divisible by 4. We can't do anything to simplify this. No. So again then, we're going to go back to our idea of splitting n, which n is an integer, to even and odds, right? So n could firstly be, well, firstly, our first case, n could be n is even, right? So then n can be written in the form of 2k. Okay, then we need to consider n squared of 2, as that's given to us here. So therefore n squared of 2 is going to be 2k all squared of 2. If we expand that, we get 4k squared add 2. Okay, well then we need to show it's not divisible by 4. Well, this thing, 4k squared, is a multiple of 4, right? It's 4 lots of k squared. But we then add 2 on. Well, if we add 2 on, it's actually just 2 more than a multiple of 4. So n squared of 2 is 2 more than a multiple of 4. But therefore then, it isn't just divisible by 4. So therefore isn't divisible by 4. Very simply, that's because you can't just factorise 4 out to everything, right? If it was divisible by 4 again, we'd be able to multiply 4 nicely out of every term. So if we were to factorise 4 here, say, we would get 4 lots of k squared. But then, if we factor the 2 out, get 4, that'd be a half, right? But then that's not an integer. So therefore and obviously n and n squared of 2 has to be an integer. So if we get any fractions, well then therefore we can't factor a 4 out, so it's not divisible by 4. But hopefully you recognise if we're adding 2 on, then it's just 2 more. And if it's 2 more than a multiple of 4, has a remainder of 2, so it's not divisible by 4 exactly. There we are. Okay. Let's have a look at this example there. The other case then, well, if n is even, well, the other possibility is n is odd, right? Okay, well, if that happens, well then n can then be written in the form 2k add 1. I should probably also say it's about k is integer. Or an integer, I guess, to be a bit more correct. But they're slightly lenient with that, I know what you mean. But anyway, n can be written in this form, because it's odd, as then our expression n squared of 2 is going, if I substitute n in literally like this, we get 2k add 1 all squared plus 2. If we expand that bracket out, you can get 4k squared, then 2k and another 2k would be plus 4k, then 1 squared would be plus 1, plus 2, then we can simplify that a little bit to get plus 3. Okay, but then again, notice if we we can factorise the first bit by 4, but then we have them plus 3. So in this case, it's 3 more than a multiple of 4. So n squared of 2 is 3 more than a multiple of 4. Right, again then, because we can't factorise 4 out of everything, because we have this remainder of 3, it's 3 more than a multiple of 4, so it isn't divisible by 4. And I should probably say as well, to be very clear, something being divisible by, say, 4 means it has to be a multiple of 4. Say if we had 4m, some number m, that's divisible by 4, because then if we then divided both sides by 4, well, it's not an equation, divide it by 4, we get just m, but that's still an integer. And so yeah, very simply then, if something is divisible by something, then it's the same as being a multiple. But yeah, okay. Let's have a look at this question then. So we need to prove that for all positive integers n, so again that means 1, 2, 3 and so on, that this expression is divisible by 6. Okay, so you're probably thinking, okay, well then let's split it to even and odd again. Let's then say n is even. Okay, well then this whole thing then will be 2k all cubed, add 3 lots of 2k all squared, add 2 lots of 2k, oh, and if you do that, you get 8k cubed, add 12k squared, add 4k. The best we can do here is probably factor out a 4. It's the highest number we can factor out, right? So then you'd get 2k cubed, add 3k squared, add 1. But really, this doesn't prove it's divisible by 6, but we need to show it is. But here we only showed it's multiple of 4. So really this is where the method fails, so we can't then consider even and odd. So then what do we do? Well then, in this case, and this is why I said do even first, because it was quite quick we could get to this point where we can realise, oh, we can't prove it this way. So we have to look for a different way, and that's where then we could stare at the the original expression, which was n cubed add 3n squared add 2n. Can we do anything with this? I think we can. We could attempt to factorise an n out firstly. N and n squared add 3n plus 2. Well, this is a quadratic then. I can try to factorise that out, right? If I then factorise it over here, well again, in order to factorise the quadratic, we need two numbers that multiply to get 2 and add to get 3. So factors of 2, 2 and 1. Well, there we are. If we add them, we get 3. So those are my factors. So we can factorise this to n of n plus 1, n plus 2. Okay, so if we stare at it, let's think about what this is saying. Well, these are essentially 3 factors, right? And n is an positive integer, right? It goes from 1, 2, 3 and so on. Well, if we have a number n, then we have the next number and the number after that as well, right? Plus 1 and then plus 2. If we think about it more, surely then, well, it's 3 numbers in order, right? If we have n, then n plus 1 and n plus 2. We can consider that as like, 3, like a 3 times table, right? If we consider 1, 2, 3, and then the next 3 numbers, 4, 5, 6, right? Then no matter what, has to be a multiple 1, a multiple 2, and a multiple 3, right? because it's three numbers consecutively, right? So we can consider it in that way, by considering, well, it has to be multiple 1, 2, and 3. Any number n, right? Um, and so then if you think about it, this has to be, this whole expression, it's three factors, right? It's three numbers multiplied together, but we're multiplying three consecutive numbers, which means numbers that are net one after another. So again, because it's three numbers listed together, you can think, if you write the list of numbers, the integers, again you'll get numbers that are multiple 1, 2, and 3. So these have to be a multiples of 1, 2, and 3, right? Well then, if they're multiples of 1, 2, and 3, therefore they're multiples of 1 times 2 times 3, right? Because that means 3, 2, and 1 go into whatever this whole expression is. So it goes into 3 times 2 times 1, right? Multiples of 1 times 2 times 3, which is 6. Well, there we are then. We therefore can say it's divisible by 6 by that logic. So therefore, n cubed 3n squared add 2n is divisible by 6. As we then discussed, that as we can factorise it into like the three consecutive integers, whole numbers, we then deduce it has to be a multiple 1, 2, and 3. So because it's three numbers together, that means it has to be in the times table 1, 2, and 3. And there we are. So therefore it's multiples of all three numbers, so you could times them together, and so overall it has to then be a multiple of 6, and therefore divisible by 6. So there we are then. So that's a very, very tricky one. Very tricky one. This was the last question in that paper. Very tricky question, that is. But again, the idea, if you can't do the usual method of perhaps even and odd, or whatever else, then look at the expression and see if you can do anything with it. In this case, I spotted I could factorise, and then I went from there. And it's helpful to consider it as factors as well, like here, like I've done here. And so yeah, so yeah, it's quite a tricky one, that is. But again, if our usual method breaks down, then try and see what you can do with the expression. But oftentimes that's a very rare type of question. Not a nice question, but very rare one. Very rare one. But yeah, I thought I'd include it just to cover all bases. Okay. So have a look at this question then. So it says use algebra to prove that the square of any natural number. So again, those on positive integers 1, 2, 3, and so on. Prove that any square of a natural number is either a multiple of 3 or one more than a multiple of 3. So again, a square of any natural number, so if n is a natural number, then we have n squared, right? So again, n can be 1, 2, 3, 4, 5, and so on. So we then consider n squared. But we can't do anything with that, right? So let's consider odd and even. So we consider if n is even, then that means we can write n in the form 2k. Again, multiple 2. Therefore, then n squared is 2k all squared, which is 4k squared. Well, again, then we fall into the same trap. It says it's a multiple of 4. Lots of cases, it's a multiple of 4, but that's not what we're asked to prove. It's either multiple 3 or one more than a multiple 3. So again, we're a bit stuck. We can't prove what the question's asking us to prove. So again, we then can't consider even or odd, and we can't do anything to this expression n squared. It doesn't really tell us anything either. We can't factorise it any further. So we need a different approach. And so what we're going to then consider is these cases instead. Instead of even and odd, oh, well, we haven't. Instead of even and odd, the question is kind of hinting talking about multiples of 3. So what we're going to consider is, and very kind of similar-ish to the last question, uh, instead of considering even and odd, which basically means we're going to consider if it's a multiple of 3 or not instead. So that means we get 3 cases, right? So if it's a multiple 3, it can be written in the form 3k. But then it could be one more than a multiple 3, so 3k add 1, or 2 more. Now you could go 3 more after that. 3k add 3, but then you're adding 3, so that's then also multiple 3, which then is that situation. And then if you did add 4, well, that's add 3 add 1, so then you'd get to that situation. So really, if we want to express a number as a multiple of 3, then we can consider these 3 cases where it's either multiple for exactly 1 more or 2 more. Okay, and again, it goes back to that list of numbers we talked about in the last example. If we have 3 numbers, then it can either be multiple 3, one less, or 2 less, and vice versa. Because obviously it goes in 3s, right? The times table of 3 goes in 3s. So therefore there are 3 possibilities: 1 more, 2 more, or exactly 3. And again, when we consider even and odd, well, that's very similar, really, actually. When we discussed even and odd, well, really, that's discussing whether it's a multiple of 2, so 2k, or one more than a multiple of 2, really. So really, when we looked at the early examples of even and odd, which you're used to, it's kind of very similar, really. Is that instead of talking about the 3 times tables, we talked about the 2 times tables. So it's either multiple 2 exactly or one more. If we had then 2k add 2, well, again, that's just a multiple 2 because you're adding on 2. So again, we only consider these 2 cases that are to do with the 2 times table. So now we're going to look at the 3 times table instead, because the 2 times table isn't helping us. So the 3 times table instead, so multiples of 3k, or 1 more or 2 more. Let's consider that then. So then we have 3 cases. So firstly, again, the easy case, n is multiple 3. Then that means n can be written in the form 3k. Again, k is an integer. Therefore, n squared is now 3k all squared, which is 9k squared. Well, what do you know? I can factor a 3 out in this case. So 3 lots of 3k squared. Therefore, n squared is now a multiple 3. So we're getting somewhere. Because that's one of the criteria, right? We want to show that it's a multiple 3, the square of a integer. So there we are then. So then we got the second case. I'll do it here. Actually, I'll do it up here. Case 2. I don't know how much room I got. Then n. Well, if again we go back to these 3 numbers, then the other possibility could be it's one more than a multiple of 3. Okay, so then we can say that n is one more than a multiple 3. So a multiple 3, 3k, and then add 1 to it. Okay. Therefore, then n squared in this case is then 3k plus 1 all squared. So then we expand that, we get 9k squared. Add 3k, add 3k, 6k. Add 1 squared is 1. And again, we're looking for multiples of 3, so let's try and factor a 3 out wherever we can. So we can factor 3 out here to get 3. Lots of 3k squared, add 2k. And then we add 1 at the end. Well, there we are. Because that's one more than a multiple of 3. So n squared is also one more than a multiple of 3. So we're really cooking with gas now. So there we are. And the last case, we do it down here. Well, we've discussed that if it's multiple 3 or 1 more, then we need to discuss if it's 2 more than a multiple 3. Okay, there we are. So therefore then we can say that n we can write as a multiple 3 and 2 more, so plus 2. Therefore n squared is going to be 3k plus 2 all squared, and so that's going to get us, if we expand it, 9k squared. 3k times 2 is 6k, another 6k would be 12k, and then 2 times 2 is 4. Okay, so then I'm going to try factor a 3 out, but I can factor it, okay, well I can factor a 3 out here. I know what, I can jump the step here, but I'm going to go through this way first. So I'm going to factor a 3 out here, that's obvious, because then I can factor a 3k squared, add 4k, add 4. Now, that doesn't prove that, well, you might not see that it is, say, a multiple 3 or 1 more than a multiple 3. Because we have a plus 4, not a plus 1 or anything like that. So, but, can I not split up the 4? Keep in mind, I want 3s. I can split the 4 up into plus 3 plus 1 and factor that in as well. So then I get like 3 lots of 3k squared and 4k. Add another, include the 3, and then add the 1 outside. There we are. Yeah, so there we are. So then, hopefully then you can see that we have a multiple 3. This whole thing inside, we don't care, it looks like a quadratic, we don't care what it is. But it's 3 lots of something, right? 3 lots of something. So it's a multiple 3, and then we add 1. So therefore n squared is also 1 more than a multiple 3. But therefore then, that's case 3 there. Therefore, those are the only 3 cases that n can be, and in every single case we saw now, it's either a multiple 3 or 1 more. So therefore we proved the question. So therefore the square of any natural number, which again is just a fancy way of saying positive integer, is a multiple 3 or 1 more than. Okay, cool. Now, obviously there's a lot of writing. In an exam you could probably get away with just roughly jotting down n is 3k, n is 3k plus 1, and n is 3k plus 2. You don't have to do the fancy layout that I've done here. Let's say case 1, case 2, case 3, because especially when you get 3 cases, it can be a bit of writing for only like 3-4 marks. So you can just probably get away with just saying n is 3k, n is 3k plus 1, n is 3k plus 2, and then go from there. And then obviously write your ending statement at the end, what I've done here, relating back to the question. But there we are then. So yeah, so sometimes then we can't just do even and odd, but even and odd, like I just said, essentially is just thinking about the 2 times table. You either get 2k, a multiple 2, or 1 more than a multiple 2. If you have 2 more again, then that's still a multiple 2. So sometimes we can't consider the 2 times table. We might need to consider, say, the 3 times table. Depending on you know, just how it works out. But yeah, let's move on to another question then. This time we need to prove that all cube numbers are either a multiple of 9 or 1 more or 1 less than the multiple of 9. Okay, so firstly cube numbers. So we have n, which is an integer. It doesn't say it, but that is what the question is implying, because it's talking about cube numbers and being multiples of 9. Anyway, n is an integer, so therefore we want to consider n cubed. Right? So n cubed then, it wants us to show that it's a multiple of 9 or 1 more or less than 9. So if we were to think about the 2 times table, so even and odd, so if we said n is even, then n can be written in the form 2k. If we then did 2k all cubed, That'd be n cubed then. That would be 8k cubed. Now that's a multiple of 8, but that's not what the question's saying. It's talking about multiple of 9 or 1 more or less. So we can't go through that approach either. So what we're going to do then, well, and we can't do anything with n cubed. We can't factorise or simplify it in any way. So again, then we're going to need to consider a bigger times table to work with. So not the 2 times table, maybe the 3 times table. Okay, so then we consider multiples of 3. So that means n could then be 3k, 3k add 1, so 1 more than a multiple 3, or 2 more than multiple 3. So there we are then. So then we got the, let's consider the first case, when n is 3k. Right, so if n is 3k, then that means, and I'm not going to write the fluffy writing now, I'm just going to say n is 3k. Therefore then, n cubed is going to be 3k all cubed, which is 3 times 3 times 3, which is 27k cubed. But I can factor a 9 out, right? So that'd be 9 lots of 3k cubed. Well, there we are then, it's a multiple of 9. Cool. Okay, second case then. Well, we discussed when n is 3k. What about if it's 1 more? So n is 3k plus 1. Then n cubed is then going to be 3k plus 1 all cubed. Which, if we expand that, then it's going to be 3. Okay. I'm going to probably do this a bit step by step. So 3k cubed is 3k plus 1, 3k plus 1, 3k plus 1. Okay, so let's expand the first 2 brackets first. So that's going to be 9k squared and 3k add 3k plus 6k, add 1. Then times that by 3k plus 1. Then we're going to get 9k squared times 3k be 27k cubed. And then 9k squared times 1 is just 9k squared. 6k times 3k is plus 18k squared. And 6k times 1 is just 6k. And then 1 times 3k is 3k. And 1 times 1 is 1. So if we simplify a little bit, collect the like terms, we get 27k cubed. 9k squared at 18k squared is 27k squared. 6k to 3k is 9k. And then we add the 1. Okay. Well then, we can factor a 9 out in the first, in all the k bits, right? So we factor a 9 out. So then that'd be 3k cubed, add 3k, add k, and then we add the 1 outside. Well, therefore, it's a multiple of 9. This whole thing is a multiple of 9, and then we add the 1 at the end. So it's 1 more than a multiple of 9. Well, there we are then. It's 1 more than a multiple of 9, so we're getting somewhere. Cool. And I need more room. Therefore, n cubed is 1 more than a multiple of 9. Right. Might need to do this to the side somewhere. I'll do it to the side here. Okay. Okay. So case 3 then. So we discuss if it's multiple 3 or 1 more. Well, then it could. The only other case if it's 2 more than a multiple 3. There. And there we are. So then n cubed, which is what we're considering, is going to be 3k plus 2 all cubed. That's going to be 3k plus 2 times by itself 3 times. If we expand that out then, well, firstly the first 2 brackets would be 9k squared, and then 3k times 2 is 6k, another 6k would be 12k, and then 2 times 2 is 4. 3k plus 2. Then if we expand that out, well, 9k squared times 3k is 27k cubed. 9k squared times 2 is 18k squared. Then 12k times 3k is 36k squared. And then 12k plus 2 is 24k. And then 4 times 3k is 12k. And then 4 times 2 is 8. And then if you collect the like terms, we get 27k cubed, and then 8k cubed and 36k k squared, sorry, and 36k squared is 54k squared. Add 36k, add 8, and we can factor a 9 out in the k terms. So 9 of 3k cubed, add 54 divided by 9 is 6. So 6k squared, and then that'd be 4k, and then we add the 8. So the 8 then, obviously that's not one more or anything, but I know it's 8, well it's just one less than 9. So, remember our question is talking about one more or one less than a multiple of 9. Well, one less than a multiple of 9, maybe. So we want to get the number at the end as a multiple of 9. Oh, hang on. Let's try and write the 8 as 9 plus 1 instead. 9 minus 1. Okay. So then I can factor the 9. If I add the 9, I can factor that 9 in the brackets too. To then get 9 of 3k cubed, add 6k squared, add 4k, add 1 minus 1. And there we are then. So therefore it's 1 less than a multiple of 9. So n cubed is 1 less. But therefore then, all 3 cases are correct, right? That satisfies what the question said. So overall then, therefore, every cube number, let's go back to the question again. Every cube number, so all cube numbers are either multiple of 9, 1 more or 1 less than 9, okay? So every cube number is either multiple 9 or 1 more or 1 less. Than a multiple of 9. And there we are then. Okay. Yes, so there we are. That's proof by exhaustion. Hopefully those examples were useful. So yeah, I guess to round up, I think probably the thing that most students struggle with the most and what they freak out about is oh, do I consider even numbers, odd numbers, or do I consider multiples of 3 or whatever? And I guess my answer and strategy is, well, first of all, again, reminder, even and odd numbers, you're just considering the 2 times table again. All I've done here is, instead of the 2 times table, I consider the 3 times table for these type of questions here. So again, my strategy then is, if you can't do anything to the expression, say n cubed here, nothing I could do there. And very often they do want you to just consider multiples of something. So 3, for instance, or 2. Try multiples of 2. And that's why I said at the very start, when you're considering even and odd, do the even case first. Because expanding 2k cubed is a hell of a lot easier than 2k plus 1 cubed. If you then expand the first one, that, as we saw, that doesn't work. So very, very quickly then, you'll be able to rule out, oh, I can't do evens here. I can't do multiples of 2. Then you consider the next number up, which is a multiple of 3. And therefore it worked. And that, we can see that works because it's talking about multiples of 9. Well, when we know 3 goes into 9, so considering the 3 times table will be very helpful there. But that is my strategy to avoid getting freaked out. If you see, oh god, it doesn't work for even numbers, well, okay, it doesn't work, don't freak out. Then try the next times table. Instead of 2, try multiples of 3. And then, again, remember, if you have 3 times table, you could either have multiples of 3, 1 more, or 1 or 2 more. Okay, because remember, 3 times table have 3 numbers, so you can only have 3 possibilities. If we say, for example, if we need to consider multiples of 5, for instance, and there was an exam question about that, then it would be n, you can write as 5k, so if it's a multiple of 5, it's 5 lots, or 1 more than 5, or 2 more than 5, or 3 more than 5, or 4 more than 5. And again, that's 5 numbers. So again, a 5 times table, those are all the possibilities that you consider. If you then did 5k at 5, well, 5 is a multiple 5, so you get back to here. Okay. So yeah, but in general, that is my strategy. Try even and odd and do even first. If that doesn't work, then do the next times table. Try multiples of 3 or 1 more or 2 more instead, right? Like we did here. And then you'd be able to tackle pretty much all the questions there. But yeah, that's my strategy. But that's proof by exhaustion then. The idea is that we split possible values into different cases, and we prove it works for all the individual cases, as it's a lot easier to do it that way than to just do it as a whole. But there we are then. So then what we're now going to move on then, I'm going to get rid of this now. What we're then going to move on now is looking at actually disproving statements. So I talked in the last time when we looked at proof last video that we have a conjecture and a theorem. A theorem is a statement, a mathematical statement that is fact. It's proven, right? There's a proof behind it. A conjecture is something that hasn't been proven yet, but we might think it's true, but we need to give a proof. But the idea is it might not be true. So in that case, when we want to prove statements or things that are not true, we need to think of a counterexample. Because if it doesn't work for a particular example, then it just doesn't work, okay? So it's not satisfactory, so therefore then it's false. So it cannot be a theorem, it can't be proved. If there's a counterexample that says, no, it doesn't work here. So that we can do it that way as well. So some questions might ask us to find a counterexample to disprove a statement. So let's have a look at some here. First of all, we want to prove that the following statement is not true. The sum of 2 consecutive prime numbers is always even. And I think with these topics, when you want to find an example, try and think of the first, like the lower numbers, the first few numbers maybe. So in this case, the first few prime numbers. So we could take a prime number p is 2, and then the next consecutive number would be 3. Then if we add them, 2 add 3 gets us 5. Well, hang on, that's not even. 5 is not even. Therefore, statement is not true. So we disproved it. Particularly when p is... when we have 2 and 3. Okay? Because remember, 2 and 3 are prime numbers as well. But there we are. So fairly simple one, right? But that's the idea. We think of an example. Sometimes it helps to think of the lower numbers, right? You know, just the first few prime numbers, for instance, and then you check that check if it works or not. And in this case, it didn't, because it didn't get us an even number, so it just isn't true. So the statement is false. Okay. Let's have a look at these ones then. So I picked a few more to try here from the textbook. So firstly, if n is for part A, if n is a positive integer, then n to the 4 minus n is divisible by 4, or in other words, a multiple of 4. So it says n is a positive integer, which again means n could be 1, 2, 3, and so on. So again, let's consider the first few numbers, right? Let's say if n is 1, then we get 1 to the 4 minus 1. That's going to get us 0. Well, actually, 0 is divisible by 4, right? 0 over 4 is still 0. 0, it doesn't work for 1. What about when n is 2 then? Then we have 2 to the 4 minus 2, n to the 4 minus n. So that would be 2 to the 4 is 16. And then the 16 take away 2 is 14. But hang on a minute, 14 is not divisible by 4, right? 14 is not divisible by 4. So statement is false when n is 2. Okay, and so the statement is false, full stop. Okay, it doesn't work for one example, just it's wrong, full stop. Okay, part B then, we then have integers always have an even number of factors. Okay, so again we're going to consider the first few numbers again. So integers again are 1, 2, 3, 4. Obviously, you could have 0 minus 1, but I think it's easier to consider from 1, I think, probably, and so on. So then, if we consider when we have 1, so I'm going to say, I'm going to say try 1. So if I do that then, well then the factors of 1 are just 1. Well, actually, there we did it, right? The factors of 1 are just 1. That's an odd amount of factors, because it's just one factor. Therefore, and by the way, I should say, the factors, what they mean here is positive factors. Obviously, you could have plus or minus 1, but it's a bit of a grey area, because you can have... I'm not going to get too deep into it, especially when you look further into maths. You can look at different types of factors. You can have rational factors. You could have surd factor. You could have complex factors. Obviously, you don't look into that, but we do have a cut-off point. And for this question, I did check the answer to this. They do consider positive factors in this case. So the only positive factors are 1 in this case. So therefore, which is 1. So 1 has an odd number of factors. So statement is false. You could also try, if you weren't satisfied with that, well, 2, because 1 is a bit funny, right? You might, 2 has 2 and 1, that's even. 3 has 3 and 1, that's even. But 4 has 4 and 1 and 2 and 2. Well, the factors are 1, 2, 4, which is odd as well. So you could have 4 as well, because there are odd numbers of factors of 4. But there we are. Okay, then part C. We have 2n squared minus 6n add 1, and we want to show that this expression is positive for all values of n. So again, we're going to try the first few values. So let's say n is 1, so I'm going to try n is 1. So if we get n is 1, then 2 lots of 1 squared minus 6 lots of 1 plus 1. Put that in your calculator, say. We get 2 lots of 1 squared. Well, what do you know? You get negative 3. Well, that's not positive. So therefore, 2n squared minus 6n is negative when n is 1. Therefore, statement is false, because we found a counterexample to disprove that it isn't always positive. There we are then. Then part D, I might need to make some room. I'll do it over here. Part D, we have 2n squared minus 2n minus 4 is a multiple of 3 for all integer values of n. So again, let's try n is 1, say first. Then we get 2 lots of 1 squared minus 2 lots of 1 minus 4. That will get me, that will be minus 4. Well, there we are then. 4, or negative 4 even, that's not a multiple 4, multiple 3. So therefore, so again, statement is false when n is 1. So the statement is false again. So again, we found an example, an integer value of n, which is 1. That means it it is not a multiple of 3. So there we are. So hopefully you get the sort of gist, right? The idea of finding a counterexample isn't always easy, perhaps just say the first few numbers. Depends on the question, but we'll look at more examples in a minute. And it won't always be to do with integers, but generally it helps to find the first few numbers, right? And you can see here, then we found an example to disprove them all. So yeah. So hopefully you get the idea. The idea of all this, finding a counterexample to disprove what we think might be a fact, like a certain statement we want to prove is false or positive. But if we find a counterexample, then the statement is false. There we are. Let's have a look at this question then. In this question, P and Q are positive integers with Q greater than P. So we have to bear that in mind. Statement 1, Q squared minus P squared, P cubed, cubed, is never a multiple of 5. Right, okay. Show by means of a counterexample that it's not true. So Q cubed minus P cubed is never a multiple of 5. So obviously we need to find integers P and Q which give a multiple of 5 if we calculate that. Right. Okay. Well, you could perhaps take, say, Q is, well, let's try it, right? Q is 2, P is 1. Then Q cubed, well, that'd be 2 cubed, take away 1 cubed. Well, that turns out to be, put that in the calculator, 7. So that's not a multiple of 5. Maybe Q is 3. P is 1. So 3Q take away 1 cubed. So that's going to be 26. Then what about when Q is 4? Then we get 4 cubed, take away 1 cubed. 4 cubed, take away 1 is 63. Okay, so that's not going to work. So then what we could do then is just plug in, increase the value of Q, and see eventually, do we get a multiple 5? So what about 5 cubed, take away 1? That's 124. Nope, 6 cubed. We get, we get 215. So when we then try Q is 6, P is 1. If we try it in the calculator, we get 6 cubed, take away 1 cubed. That comes out to 1215. Now that is a multiple of 5. So if, I'm going to write down here, if Q is 6, P is 1, and that satisfies the condition, they're both positive integers, and Q is bigger than P. 6 is bigger than 1. So that's valid. So if we pick that, then 6 cubed, take away 1 cubed is 215. So 215 is multiple 5. So statement is false. Because we found this is counterexample. Okay, cool. Okay, then part B, which isn't a counterexample, but it's just using what we just learned in the previous about exhaustion. When P and Q are consecutive even integers, Q cubed take away P cubed is a multiple of 8. Okay, so you might think, well, even and odd, but actually they tell you what to consider in this case, and they make it a bit easy for you. They tell you that P and Q must be consecutive even integers. So, and we also know that Q has to be bigger than P. So firstly then, if P small, so take P then, if they're both even integers, so firstly we can write P in the form 2k. Now Q is also even, but it's a consecutive even. Consecutive numbers means the next one. So we want the next even integer after P. Well, if it's 2k, then the next multiple 2 is 2k add 2. So Q will then be 2k add 2. So those are what we consider. So therefore then Q cubed, take away P cubed in this case, is going to be 2k plus 2 all cubed, take away 2k all cubed, and so then we need to expand the bracket. So firstly, that's 2k plus 2 times by itself 3 times. Oh, that's a 2. Take away, and I can expand this quite easily. 2k all cubed is 8k cubed. So if we expand this then, so the first two brackets would be 4k squared, and 2k times 2 is 4k, another 4k would be 8k, then 2 times 2 is plus 4, times by 2k plus 2, the other bracket, and then we get, then that's also take away the 8k cubed. If we do that, then we then get 8k cubed, and then 4k squared times 2 is 8k squared, then 8k times 2k is plus 16k squared, 8k times 2 is plus 16k, then 4 times 2k is 8k, then 4 times 2 is 8, and then we have the 8k cubed outside. Then we simplify the terms. So firstly, we have 8k cubed, but then we minus 8k cubed, so that will go away. Then we got 8k squared as 16k squared, that is 24k squared. Okay, then we have 16k and 8k, that's also 24k. Then we have the plus 8. So that's what we're left with. I can, okay, what's it asking? It's saying that it needs to be a multiple of 8. Well, that's good news, because I can factor out an 8 in all the terms. So 8 lots of 3k squared and 3k plus 1. Well, therefore then, that's a multiple of 8. This q cubed minus p cubed is indeed a multiple of 8. And that's a multiple of 8 when p and q are consecutive even integers. And there we are then, proof done. So yeah, as a reminder, probably the difficulty with this question is actually realising the consecutive. So remember, consecutive again, you need to then consider the next number after. So for 2 times table, for instance, 2, 4, 6, 8. Well, if we have 2, then the next one before. So we add 2. Okay, so that's where we've got here for p, which is a multiple 2. Then the next multiple 2 would be add 2 to that. So yeah, don't get caught up on that. But yeah. And also, if you're struggling with brackets as well, again, don't be afraid to do it aside on the page somewhere, right? And do it step by step. Okay, do it term by term if it helps you. Because again, it can be quite tricky algebra. It might be easy to make a mistake or miss a term out, something like that. But there we are then. So we get our answer in the end. Cool. So again, a reminder, that is now a proof by exhaustion. Well, it is a proof by exhaustion because they can tell you what case to consider. But yeah, it's an example of the work we looked at just. So yeah, hopefully you're more comfortable that sort of question now. Okay, we've got another exam question. If we got numbers m and n, which are now irrational numbers, and they're not equal, which is what that means, then the product mn is also irrational. Disprove this statement by means of a counterexample. Now, obviously the key idea with this question, you need to know what irrational means. So that simply means a number that isn't rational. So it's a number that cannot be written as a fraction, basically. And by fraction, I mean a fraction with integers in the top and bottom. So a fraction of integers. So for example, 2 over 4 is an integer. Minus 5 over 17 is an integer. But pi over 2 isn't an integer. Nor is pi over 1, which obviously goes to pi. That's not a rational number because pi is irrational. So both the top and the bottom have to be integers, okay? So that's what that means. And so the examples of irrationals are going to be pi. And also root as surds as well. So that's going to be like root 2, for instance. Okay. Remember when we looked at surds, even at GCSE, that is an irrational number as essentially, put that in a calculator, you'll get an ongoing infinite decimal. And so we can't write it as a fraction of integers. So we're going to bear that in mind because those are examples, right? We could use that potentially as examples here. Those are irrational numbers. So, okay. So m and n are irrational numbers, then the product is irrational. Let's take m to be, pi. That's irrational. Okay, well then we have we can kind of, n, the other number, I don't know at the moment, but we'll know that whatever this n has to be, that mn has to be, it has to be, we want an example of m and n where it's not irrational when the times together, because that'd be a counterexample. So if we had mn, that's pi times something, and that cannot be irrational, so it has to be a fraction or an integer. Well, can't we be a bit crafty here, and instead of having, and the other number, couldn't that just be 1 over pi? And so then we get pi over pi, which cancels with just 1, which is rational, right? But there we are then. And then the other number, then we can just take to be 1 over pi. So then we times them, and then it cancels each other out to get 1. So there we are then, we've got our counterexample. So therefore, the statement is false here. Right, because we picked 2 irrational numbers, and they times to get 1. Because we were quite crafty with the example, because we picked them to be reciprocal, so they cancel each other out in this way. So the statement is false here. So there we are. And that's it then. For counterexamples, we will look at some more in the next bit. But the next bit, in the final part of the proof, we're going to look at, and it's quite a weird one. It's to do with inequalities, and we can prove certain inequalities with algebra, like this. Okay. Now, there's not many questions on this, but I thought a dedicated section to it. The idea is, you want to prove a certain inequality with algebra like this. And from what I've noticed, there's a very particular way they do it. You need to eventually consider the expansion of 2 numbers squared, right? So a plus b squared, which you should know is going to be a squared add b, add ab, which should be 2ab, add b squared. We're gonna be using that sort of formula, which is going to be quite key to these sort of questions, because eventually we can start to use that formula. But I'm going to go over an example first then, and we'll talk more about that in a minute. Firstly, we need to prove that x over y add y over x is greater than or equal to 2. Now, where on earth do we go from here? Okay, so with this sort of question, it's a great idea to firstly just see what happens if we add the fractions, right? Let's see how far we can sort of simplify this inequality. If we add it, firstly, if we add the fraction, we're going to get x squared add y squared over xy, right? If we add the 2 fractions together, and that'd be greater than or equal to 2, right? That's just adding these fractions together. Remember from GCSE, we can add algebraic fractions, like with ordinary fractions. The idea, we look for a common denominator and then add and then go from there. Anyway, we get to that point. Then we can times across to get x squared and y squared is greater than or equal to 2xy. Now, we are timesing by a number xy, right, to both sides. That's what we've done, times by xy. Now that you'd be right to be concerned about the inequality, the direction, because if you have a negative number times, then that would reverse the inequality. However, x and y are given to be positive, so therefore their product would be positive. So we times it by positive there. So there's not much to be concerned about there. Right, okay. I guess perhaps then we could take away 2xy. So x squared and y squared take away 2xy is then greater than or equal to 0. Now, we can't really do anything at this point, but hopefully you can kind of spot I could factorise this, but it's very ugly because I have an x and y. That's where these formulas are going to help. We're going to consider x plus y squared and x minus y squared, either or, right? If we consider these two expansions here, well, the x plus y squared for any x and y, right? X squared add 2xy, add y squared if you expand that. And this one would be x squared. Now that would be x, then take away xy, take away xy, would be take away 2xy, add y squared. So they're very similar, except from you adding 2xy here and taking away there. Well, hang on, isn't this whole expression this? So we can substitute that in. So therefore, x minus y squared is now greater than or equal to 0. And that makes sense, because this is now a square number. And we know square numbers has to be at least 0. So there we are then. We reached something that we know is a matter of fact. So that has to be true. However, that's the idea of the proof. That is the idea of the proof. But the problem is, if we wrote it in this way, with a proof, remember we talked about last time, you have to start with something we know is true and then work our way to the statement to prove it. What we've done here is we've started with the statement we want to prove. We don't know if this is true. This is what we're proving. We can't start with something that we don't know is true. So we need to go the other way, because we know this is definitely true, the bottom bit, because it's a square number. That's above 0. It has to be. So what we're going to do then is to write it properly. Then we're going to start with x minus y squared greater than or equal to 0 instead. We're going to start here first, and that is our statement that we that is our factual statement that we're going to start with, right? And then we're going to just reverse the proof essentially. And we know that's true as square numbers are non-negative. Okay, so they're at least 0. So they can't be negative. Then we're just going to reverse engineer. So then we can expand the brackets to get x squared minus 2xy plus y squared is greater than or equal to 0. Then we can add the 2xy to both sides. Then we're going to divide by xy. And again, likewise with times in, dividing, it's positive, so it will keep the direction of the inequality. So we get x squared and y squared over xy is greater than or equal to 2. Okay, then we can split up the fraction to then get x squared over x, add y squared over y is great, xy, 2. And then we can just simplify the fraction to get that, therefore x over y add y over x is indeed 2. And that's our proof, okay? There we are. So it just went backwards. And so that's the idea of these sort of questions. They're all a bit weird, these questions, but that's the same, that's the strategy, right? Is that you use the inequality given to aid you to see where you need to end up by just simplifying the fractions, right? And we're going to need to consider either these two expansions here, right? That will be coming in clutch with these questions. Eventually, you will need to use either these results, right? A square bracket, right? The idea is because a square bracket has to be above 0. That will tell us an inequality straight off the bat, right? Yeah. So that's the idea. So then we'll do more, obviously, in a moment. But for part B, then it's asking simply to use a counterexample to show that this is not true when when x and y are not positive. Right. So here, it says it's not true, and they're not both positive. That suggests that one could be negative, at least one of them negative. Let's try then, x is 1, but then y is negative, so say minus 1, right? So they're not both positive. Okay, let's try that. So then x will be 1 over minus 1 for y, and y, which is minus 1, and x is 1. Well, that's minus 1 minus 1, right? Which is minus 2. Now, minus 2 is less than 2, right? But hang on, this expression, the x over y and y over x, has to be at least 2, right? That's the inequality. But here, we've got less than 2. So therefore, statement is not true again, right? Because we found a counterexample when x is 1, y is negative 1. And so that is my strategy as well as considering the smaller numbers, if you're a bit stuck. Consider if one of them is negative as well. Usually that's a tick with these sort of questions. Is that if you make at least one of them negative, the try, then it turns out it doesn't make it correct. You disprove it, right? So yeah, okay. Okay, let's have a look at another example here. It is claimed that the following inequality is true for all negative numbers x and y. So they want to prove this. X and y is greater than or equal to root x squared and y squared. And we get given this proof, and it wants us to first explain the error made from the student. So let's have a look. So let's go step by step. X and y is greater than or equal to x squared and y squared. Then they squared both sides. X plus y squared is that. Then they expanded this bracket to get x squared and y squared is plus 2xy is x squared and y squared. Then they cancelled out to get 2xy is then greater than 0. So then they said 2xy is greater than 0, which is true because x and y are both negative. So obviously then two negatives make a positive. So xy is positive. Now that's actually mostly all true. The problem here is what I talked about earlier. You can't start with the claim, you know. You have to start from something you know is correct. So it's, the ordering of the proof is wrong. Because again, like, you want to prove this, right? This statement. You can't start with that statement. You have to start somewhere else that you know is definitely true, and then work your way towards a statement which then proves it. So the ordering is wrong. So the error is the student should not start the proof with the claim, right? As the claim hasn't been proven to be true. And so that's the idea with proofs, right? Ideally we want to start with something that you know is true, definitely mathematically true, and then work your way back. Now, if he instead started with this bit, 2xy is greater than 0 because xy is positive, then then the student would be onto something there. But it's the wrong way around. You can't start with what you're trying to prove is true. It doesn't work like that. So that's the error. Now part B then says, by use of a counterexample, verify that the inequality is not satisfied if both x and y are negative. Okay. So actually it turns out the inequality isn't true, which again shows why you should never start with what you are claiming to be true, because it might not be true. Therefore the whole proof breaks down. Anyway, so we need to use a counterexample, specifically if they're both negative. Well, again, very simply then, let's just take x and y to be negative 1, so negative 1, right? So, very simple. Then if x and y are negative 1, then x plus y is minus 2, right? Minus 1 and minus 1 is minus 2. And and root x squared and y squared. Well, x squared and y squared, that'd be 1. And minus 1 squared is 1. So that'd be root 2. Well, then clearly minus 2. So it's saying x and y have to be greater than or equal to the root. But that's the opposite way around. Here, minus 2 is less than root 2. So x plus y is actually less than root x squared and y squared. But it's the opposite way around, right? They want us to prove it's greater than or equal to there. But here with our example, it's less than. So therefore, statement is false. When x and y are both negative integers. There we are. As that's what the question said. The question said, disprove it when both x and y are negative there. So the inequality is not satisfied. Then part B then says, prove that this inequality is true if x and y are both positive. Right, okay. So part C. Now, like I said, when you want to prove this inequality, you'd want to work backwards and simplify and undo essentially what's happened. But this proof, this proof here, is what it's doing. It's working backwards and considering, again, see, it's considering the bracket x plus y squared. That is key to these sort of proof questions with inequalities. So they've done that then. They squared both sides from line 1 to line 2. Then they expanded the bracket. Then they took away both x squared and y squared both sides. So they've already outlined the proof for us, really. So we should probably start with this. 2xy is greater than 0. Do we know that's true? Is 2xy greater than 0? Well, yes, because x and y are both positive in this case. So if x and y are positive, then we know that their product xy is positive, as x and y are both positive integers. So because x and y are both positive integers, we can start with 2xy greater than 0, which is what the student has done, right? The student ended up there, but really they should have started here instead. Then we can essentially just reverse what the student did to get back to the original inequality. So then they, what they then said, well, they considered this bracket, right? Then we need to get to x squared and y squared plus 2x. So they add x squared and y squared, right, to both sides. So then you add x squared and y squared to both sides of the inequality, as so. So I'm going to say, you don't have to say this, but I'm going to explain in words what's happening. You don't have to write this sentence I'm writing. I'm writing it for clarity, just to help. So we added x squared and y squared to both sides. What have they done then? Let's have a look. Okay, so we're at this step. Then we go to this step of x and y squared. So we're going to recognise that x plus y squared, if I expand it, it's x squared add 2xy add y squared. That's exactly what we've got. So we can sort of just substitute that in, right? To get that x plus y squared is also greater than x squared and y squared. Cool. Okay, but then what have they done here to here? Well, they've, then we can sort of square root both sides, right? I should probably say here they use x plus y squared is equal to x squared and y squared and 2xy. Okay, then we're going to square root both sides. So then x plus y is greater than the root of x squared and y squared. Now, this is why the proof failed with negative integers, because x and y originally, if they were both negative, then x and y would be negative as well. Now, if we were to square root x and y, if we square root a negative, you can't do that, right? Which is why the proof failed last time. But here we are allowed to square root both sides because x and y is a positive quantity this time, because x and y are both positive. That means that well, that means you can go and square root it, right? Because it's a positive thing. So we are allowed to do this step in this case because it's positive. So I'm going to say square root both sides because that's what we've done. And we get to that statement. Well, there we are then. So we prove the inequality then. There we are. X and y is greater than or equal to x squared and y squared. Okay, well, actually, technically, this would be greater than or equal to, because if x and y was 0, then it could be great. So we could just put an equal to sign there. It'd be completely fine. So there we are. We proved the inequality then. So therefore, inequality proved. I'm not even going to write it. That's what we needed to prove. So there we are then. So yeah, so hopefully you start to get the idea of these sort of questions now. You kind of work with the inequality, see what you can do with it, and then you will need to use the brackets here at some point. X and y squared, x squared, x and y. Oh, that should be squared there. A square bracket, which will help you simplify the inequality to see what you need to do. Okay, let's have a look at this question then. We need to prove that for all any positive integers p and q, that p add q is greater than root 4pq. Now, obviously, we can't start from this, but what we do then is kind of undo the inequality, right? Simplify it as much as we can. See where we can get to. Well, firstly, I notice I can probably square both sides to get rid of the square root. That's probably a good first step. So then p add q all squared will be greater than 4pq. Okay, then I have that bracket. Let's expand it, right? So then I'm going to have, that'll go to p squared add q squared add 2pq would then be greater than 4pq. Then we can take away 4pq to both sides to get p squared add q squared. Take away 2pq would be greater than 0. Now, we can't do anything more with that, but that almost looks like I can factorise it. And again, I'm going to consider the brackets p add q squared or p minus q squared. Now, p add q squared is p squared and q squared add 2pq. But p minus q squared is p squared plus q squared take away 2pq. Well, that's what we've got, right? We can then substitute that in to therefore get p minus q all squared is then greater than 0. And we know that's true because then it's a square number, right? Square number has to be at least 0. But there, it has to be strictly above 0 because if the bracket was 0, then p would equal q. There is an implicit assumption that p cannot be q, but anyway, we can deduce it's greater than 0 here, and that's a clear observation because it's a square bracket, right? Well, therefore, that is a fact, and then we can use that then, and then work backwards, right? So we ended up with something that we know is true, and that's the idea. See, look, the idea with this, eventually we get to a square bracket, and we get to a square bracket by using these formula, right? These two brackets that we know. So then we can work backwards, right? And then so we can start from here. So then we're going to say, well, p minus q squared is greater than 0 as a square number is positive. But then we can just reverse engineer. So then we can expand the brackets to get p squared. Take away 2pq, add q squared is greater than 0. Okay, so we've gone from this first step to there. Then we're going to need to work back up there. So then I have add p. So then I have 0 here, and 4pq here. So I'm going to have to add 4pq to both sides, and then minus 2pq will go to positive 2pq. So there we are. So then we're going to add 4pq to both sides to then get p squared plus q squared, and then minus 2pq, add 4pq, that's going to get me plus 2pq, right? So then plus 2pq is then greater than 4pq. There we are. Okay, so we got to that bit. Then we can go to that step then. And then, well, I recognise that this expression now is p at q squared, right? If I expanded that bracket, that's exactly what I get. P squared and q squared add 2pq. So I can substitute that in to then get p at q all squared is greater than 4pq. And again, as I remind you, again with these questions, we are going to be using these brackets, p at q squared or p minus q squared. You need to remember those two brackets to help you with these sort of questions. But there we are. Okay, well then the last step, I can see I need to square root both sides, right? And that's what I'm going to do. So therefore, then p plus q is then the root 4pq. And I'm allowed to square root both sides here because p and q would be positive. Because p and q are told to be positive numbers, so I'm allowed to do that here. So there we are then, that's our proof. Cool. Okay, so that's part A. Part B then says, show by means of a counterexample that this inequality does not hold true when p and q are both negative. Okay, well then again, let's just say p and q are minus 1, right? It's nice and simple. So p and q are both negative, both minus 1. Then, well, firstly, with this inequality here, p at q is again going to be minus 2 if we add them, and root 4pq, that's root 4 times pq, that minus 1 times minus 1 is just 1, that would be root 4, which is 2. Well, hang on, that means p and q is less than, minus 2 is less than 2, so p and q is actually less than root 4pq here. So the inequality is false when p and q are both negative integers. As again, we found a specific example that shows that that the inequality, well, frankly, isn't true for those two numbers. So the statement has to be false then, as we disproved it with an example. Okay, cool. Okay, I believe there's one more, two more. Okay, so we've got some exam questions on this. So firstly, we are given x and y integers such that x is less than 0 and x and y squared is less than 9x squared and y squared. Show that y is greater than 4x. Okay, so, well, actually, they kind of helped us out here. So they've told us this, so we probably should use this, right? X and y squared is less than 9x squared and y squared. Now, again, this is a bracket, and as we've seen with the examples, we should probably expand the bracket, right? So if we expand that, we get x squared add 2xy and y squared is less than 9x squared plus y squared. Now, if I take away the right side, well, x squared take away 9x squared be minus 8x squared, add 2xy and y squared take away y squared is 0, so we're left with less than 0. Right, okay. Okay. So I need to show that y is greater than 4x. Now, again, this is kind of like rearranging for y, isn't it? Y in terms of x. We're going to kind of do that then. So if we want to get y on its own, well then let's add the 8x squared back to the other side to then get 2xy is less than 8x squared. Then I can divide by 2 to get xy is less than 4x squared. Now actually it very vaguely resembles this inequality now. If I divide it by x, I vaguely get y is some lots of 4x, right? But obviously the inequality is the way around. So then we should divide by x then, right? Because then I get y and then 4x. That's what I'm going to get. Y here and 4x there if I divide by x both sides. If I do that then, well, you'd think y may be less than 4x. However, it's saying y has to be greater than 4x. Why is that? Right, again, remember, when we divide by a number to an inequality, we need to be careful about the sign of the number. If it's negative, then we need to flip the sign. Well, actually, look at this. X is less than 0. That is negative. So we're dividing by x, which is a negative number. So we actually need to reverse the inequality. And actually, instead of less than 4x, it'd be greater than 4x. And there we are. And I'd say you probably have to write a little comment here saying as x is negative. Which essentially means that we have to flip the direction of the inequality. But there we are then. Little proof there. Cool. And again, we consider the brackets x plus y squared. I'll keep iterating it so it helps, but the brackets x plus y squared and x minus y squared and their expansion, they're going to be they're proof vital for these sort of questions. It's really, really good idea to remember them. Have that in mind with these sort of questions. But yeah, there we are then. Cool. Okay, final question then. We have to prove that for all positive values a and b, 4a over b 4a over b add b over a is greater than or equal to 4. Right, okay, so again we kind of need to work and kind of simplify this inequality, kind of make, so probably best to add both fractions and see what we can do. So if we add both fractions, so we want a common denominator, so that's going to be AB. So we multiply the first fraction by A, we get 4A squared, and then we add B times B, that'd be B squared over AB. That's greater than or equal to 4. Now we can then times across by AB to get greater than or equal to 4AB. Now, it's the inequality does not change direction, does not flip because it's positive again. A and B are both positive, so if we times in by AB, AB is positive as well. So there we are. So I'll make a note there. Times by AB, that's positive, so there we are. Okay, so then I'm probably best to take away 4AB to both sides. And that's greater than or equal to 0. Now at this stage, we should probably consider an inequality. Say either a plus b squared or a minus b squared. Well, have a negative here, negative 4ab, so it's probably best to consider a minus b squared. If I do that, if I expand it, I get a squared plus b squared, take away 2ab. It's not exactly the same. I have the b squared part, but I have 4a squared in here, but I have a squared here. I still need to consider this sort of bracket, but instead of having a and then instead of just having a here, a times a would be a squared. What if I have 2a instead, right? adjust that to 2a, then 2a times 2a will get me 4a squared. Well, there we are then. That'd be 4a squared, add b squared, but then if I expand it again, 2a times minus b will be minus 2ab, but then there'll be another minus 2ab, which will get me minus 4ab. Again, if you're a bit skeptical about that expansion, do it yourself somewhere, do it term by term, you'll get that expansion. Well, there we are then. That's the bracket we need to consider. So it's a bit different, but the idea is the same, right? We consider some bracket squared, right? A plus b, a take away b squared, some amounts, right? There we are. So then we can substitute that in. 2a minus b all squared is greater than or equal to 0. But we know that's true because that's still a square number. So therefore we're going to start with that then. So 2a minus b squared is indeed at least 0, as square numbers are positive. Okay, so then we kind of just reverse back then, right? So then we expand the brackets to get 4a squared take plus b squared take away 4ab is still greater than or equal to 0. So we expand the bracket. Then we go from here to that step. So then I notice I'm adding 4ab because I'm going from 0 to the one side to then 4ab. So I need to add 4ab to then get 4a squared and b squared. Then minus 4ab, add 4ab goes to 0. So I'm simply left with that greater than or equal to 4ab because I'm adding 4ab to both sides, right? Okay, then then I need to go to then I need to go to that step, the fraction. So then I need to divide by 4. So I'll get 4ab here, then I just have 4. So I'm divided by ab here. So that's what I'm going to do. So if I divide by ab, I get 4a squared plus b squared over ab, and greater than or equal to 4. Again, the inequality stays where it is. It's because ab is positive. So then I need to end up with that bit then. That's what we started with. That's the inequality we want. Well, then the fraction split up. So let's split up the fraction then. So then 4a squared over ab and b squared over ab is greater than or equal to 4. If we then simplify this, cancel out the a, firstly we have 4a over b, and b, and then we cancel the b in the second fraction. B over a is greater than or equal to 4. There we are. I believe that's the inequality they want us to prove. Yes, there it is. Cool. So hopefully you get the gist for these sort of inequality proofs now. Eventually we can sort of simplify and work with the inequality to see what we need to consider, right? And often we do need to consider these sort of two brackets, right? A plus b squared or a minus b squared at some point. There we are. Okay, but then that's then part B then says prove by a counterexample that this is not true for all values of a and b. So okay, so we know it's true because we did prove it. It's true for all positive values of a and b. If a and b are both positive, then that's true. Now it's not true then for other values. So maybe let's take a is positive and b is negative then. Let's then take I'll do part B here actually. Let's say that a is 1 and b is negative 1, right? Then we have 4a over b, add b over a. Well, actually 4a would go to 4 over b, which would be negative 1, plus b, which is negative 1, over a, which is 4. Well, that's going to be minus 4 minus a quarter. But we know that's going to be less than 4, right? That's a negative number. That's less than 4. So therefore, it's not true. Okay, the statement is not true for other values of a and b. Okay, because we saw when b is negative, when a is 1, b is negative 1, then it's no longer true. And there we are. Cool. So that's proof then. So it can be tricky, but hopefully you've seen examples now. Uh, these are the sort of questions you'll get in the exam, right? These inequality proofs, they work the same way, you know. The proof divisibility ones that we looked at first with exhaustion, they work the same way. You consider even numbers, so there are multiple of 2, so the 2 times table. If it's not, then you maybe consider the 3 times table, and then you work from there, right? And then you consider all those cases. And then we also look at counterexamples, so again, a tip there. Look for the small numbers, or maybe consider making one of them negative. And then with the inequality ones, then you work backwards. So you kind of work with the inequality, what you can do. Then you consider the brackets, and then it works from there. So that's proof. Hopefully this gives you more confidence to tackle these questions. They are tough, especially if you haven't seen maybe the right things to do. They can be like, what do I do here? But hopefully this video has helped. But that's proof. So I'll see you next time.